Okay, little over 1 minute on the 6 o'clock. Let's get started. So today we were supposed to uh, study about this procedure implementation at the lower level. So did you guys have a chance to look at those area? Why don't I have that poll? Preparedness. Okay, let's take a minute to do that. Okay, I have the class preparedness result out of 32, I believe. 44% said all of the videos has been reviewed. That's very good. Some of them about 47%. Okay, lecture notes 59%. Okay, that's better. Some or all part, some part of it about 31%. And only one have a question. Others don't have a question or don't have question, didn't ask me. Okay, anyway, whatever the case, what is your question? Okay, Carter said about this stack pointer. Okay, arguments are stored on the stack area of the memory and how the stack pointer is used. Okay, let's do it. Let's do it next day. That is more related to that. Okay, I just started recording this session. I forgot to hit that button. Anyway, so that question, that usage of the stack memory to pass the argument and how is it accessed, we'll go over in the next lecture. Okay, that's definitely on my list. So till then, let me try to reiterate this concept of this procedure or function, whatever you want to call at the assembly level. Let's try to compare it with respect to your high-level functions. Okay, so that it start makes sense. All right, I'm sharing my Jamboard. Okay, all right. So here we are all familiar with the high-level side of the function implementation, right? Let's look at that. So my high level would be like, let's say, high level function. So what we have something like an declaration. Like for example, I'm writing in C, but I'm pretty sure Java has similar syntax. Let's say, let's talk about this, our favorite function called factorial. So we have declaration usage, maybe like inside the main program. You have code, and then you have a call to, let's say, integer r equals factorial of 12, something like that, and some code. And then you have this definition, which is like integer factorial integer n, some code, and followed by some return result. So do we all agree that this is the kind of a structure and the high level programming language, we have to have a declaration, which is usually going to header file. And then we have the usage. We have a call. This is calling the function factorial with an argument 12, value 12, and it returns result. It's storing the variable r. And then we have this part, definition of this. This is the function body, right? This is the function body. So that means that the high level programming language, it's not only a concept like reusage of the code. It is not only a concept, but it also followed through certain syntax and semantics in the grammar. However, at the assembly level or low level programming, there is neither syntax nor semantics. So no syntax, no semantic at low level programming language. All we have is the concept. So you need to grasp this idea. There is no syntax, no semantics, like you don't need to declare a function. You don't need to go with a specific syntax to define a body of a function. There is nothing such thing. It's only at the concept level. And what is that concept level? It starts with a label. It starts with a label. You can name that label at anything. And it has runtime environment storage code followed by body, which is like, if you want to make it a correspondence to the high level function, it's that correspondence followed by RT restore code, return runtime environment restore code, followed by jump register $RA. If you want to like relate that to a return, yes, questionable association of that relation, but yeah, but it's kind of saying it, okay, go back to the caller, And definitely it has an, so RT store and JR, they are going to be at least some exit level you need. Sometimes you don't need, but ideally let's put an exit level here. So fact end. So that inside the body, if it is an return time, it can call and jump into here to make the restore happen and then go back to the caller. So, and then on the main routine, like let's say you want to correspond to this one, let's say your program start with a label called main. This is the instruction, instruction, instruction. Then what we have here is basically calling a function is nothing but jump with a specified jump called JL, jump and link to the label name. Right? So this one is practically, if you want to correspondence in the high level program, this is the correspondence, JL. And then it goes with this instruction, instruction, instruction. So JR, what it does is basically returns the controls from these to the next instruction here. Okay. And hopefully somewhere down the line you have the exit. Let me write it down in a different code. Exit. For us, it's a macro. So see, like, there is nothing special about writing a function semantically or syntactically at the low level program. It is only by conception you are segregating and differentiating between parts of the body. But labels and all this stuff are pretty generic. Like you can just look at the code and tell me that this is a function, this is a loop, this is an like iterative code. You cannot tell that except only few clues, right? One is definitely, if you look at this kind of statement, JL, this is a conceptual function call. So you know this factorial, that label name factorial, is from that level, it is trying to define a function. And within the function, definitely it has these characteristics of it has to be a runtime storage code, followed by a body, followed by a runtime restore code, followed by ended with jump register, $array, always. Unless these characteristics are present, it is not a function. It is something else. Okay. Question?
I have a question.
Yes, Matthew.
So did you just say in the beginning that we're going to get into the actual frame and the stack pointer on Wednesday?
It's no, it's basically the Carter question about how these arguments are stored in the stack areas and the memory, and how the stack pointer is used to access those arguments. That specific discussion we'll make on next day. You can ask other questions.
Yeah, I think mine's different. So I'm just wondering about, so when we actually do this recursive factorial, are we pushing the stack more and more to hold the new, kind of like the frame pointer and the RA and like all these registers we have to store? Are we pushing it and storing kind of like new memory locations for them every time we
Exactly.
recursive call?
Yes.
Okay.
Yeah.
All right. Yeah. Thank you.
So I was going to come to that point. Okay, just glad that you asked, Carly. So let's look at other correspondence here also, right? For example, you are pass the arguments, right? Passing the arguments into the function on the high level. Here at the low level, we do the same thing by through these arguments register A0, A1, A2, A3, 4 arguments. And if you need more argument to pass, use a stack memory. So this part we'll discuss next, okay? But in general, I hope you guys have simple function which needs less than 4, like less than equals 4 arguments there. So this is the argument passing mechanism. So you set it, your A1, A2, or A star, I would say, that setting code goes here, setting, so before your JL, there would be some code to set these registers, whatever you need. And then you basically, like inside the function body, you access those registers to look at the argument passed by the caller, And how now the return, on the other hand, is basically done through here in the high level language, and it is being stored at somewhere in the variable, high level variable. It is used there, right? So it is kind of returning the value and storing into the high level variable R. The same thing is done here through the register V. 0, usually if you want to return more than one value, V1, okay? And if you want to return more than 2 values, you can do that with the convention that you will be either pushing something onto the stack or update some of the memories. But other than that, it's not recommended to, until it is a very special case, don't try to return more than 2 values from a function. Let's keep it simple. So what you'll do here, then you will see some sort of usage on this V star, right? Use the V star after you call is done. So sequence is like your set argument register, jump and link to that level. And then once it is coming back, control is back from that, that function, conceptual function body, you use that values written in the V registers. So that is like passing argument, getting back the values. Next part. Okay, so far so good. Any questions so far till now? Okay. Now, how about the recursive, right? Recursive call in the high level program, you see that it calls some point of time, I don't know, something like that, right? I'm not sure even this is a right code or not. Something like that. Like it calls, practically it calls itself, right? That is the recursive telltale sign of the recursive function. So here we have such a telltale notion. Like if you look at the body and if it is doing a JAL, jump and link to factorial, like same like the calling from outside, you are basically doing it from inside, right? Doing it from inside, then this is a recursive call. And in this process, you see, you basically are storing the runtime call environment. And this runtime call environment is different because in the first time when the initial call was made from the main program's runtime environment is going to be different than the factorial's body's own runtime environment, isn't it? And that's why we need to actually push new frame onto the stack memory. And that's why it will grow. It will grow usage of the stack memory. So that's why recursive function has this side effect, or has this concern, at least you need to be worried about, is that how big is your frame and how much you are filling up the stack part of the memory. In fact, I'm not sure, or at least I'm sure at least one or two of you have experienced this problem. If you are implementing a recursive function and it is unbounded recursive call, you will go into certain error like a bus error or segmentation fault at the high level program. It's practically does due to this, because with this infinite number of calls to itself, it actually grows and fill up the stack memory pretty soon. And then it basically raise an exception, and that's what the bus error or segmentation fault cause. Okay, so probably maybe you have experienced that. If you have not, just try to write an unbound recursive call and run it and see how the system behaves. Question? No question? What else shall we do? Okay, let's see. All right, how about some pop quiz? Go to your canvas and check if you can access them. Let me open up this launch. If you can find out and ready to enter the password, please say yes onto this poll.
Is it Pop Quiz 4 or something?
Yes.
I'm not seeing it on my quizzes page.
Yeah, I can't find it either.
Oh. Can you try now?
Okay, let me refresh. Oh, there it is. Okay, it's at the bottom.
Professor, I didn't get a password.
No, I haven't shared it yet.
Okay.
So you guys need to hit yes if you are ready to enter that password. Then I will open up that other poll. Yeah, let me see if I have updated the password into the poll. Seems like. Okay, 39 or 40, one more to go. But it's 2 minutes already. Okay, let me just end this poll and have the password anyway. Just hold on. 626, 626, 630, 640. Okay. All right, end polling. Okay, here it goes with that passcode, the poll with the passcode. Yeah, I see a couple of students can enter. So the passcode is good. I think most of you are done. Maybe one or two if you have like a couple of minutes there left. Um, anyway, let me open up the scores for you. Okay, so far your statistics average score is 59%, like even below pass mark. We need to work on that part. Please make sure you are prepared coming into the class uh, for the day of for the material of the day. We have high score 88%, which is not even a score. So I think as a whole class, you guys need to work on uh, these things. Okay, anyway. So basically, let's say, okay. So now let me share this other part, the whiteboard. I have a problem for you to think. Let's say I have a function. It's a factorial function uh, like this written. I think it's the same function or maybe a little bit different way it has been written. Nonetheless, it doesn't matter. This one is definitely a recursive function because I can see there is this JL calling from your body, right? JL calling from your body. So JL and name is the fact. So it is a recursive function, and let's see it has been called with a value 10 in the argument register 0. So you need to analyze this piece of code and tell me the peak usage, peak stack memory usage means what is my total memory usage. Peak memory usage means like in a recursive call, as I said, it will basically start storing frame on top of another frame on top of another frame till it actually hit the base case and then comes back from there with popping up the frames. So you need to see how much depth, max depth this recursive routine goes and what is the maximum amount of frame is concurrent in the time. Like at one point of time, maybe it's a 10 frame, 20 frame, whatever, depending on the data and the implementation of the memory of this function in the assembly code. That part will vary. So peak memory, you need to compute the peak stack memory usage for this function call, assuming you have passed 10 in that argument register A0. So you think this problem yourself for 5 minutes, and then I will open up the breakout room for you for another 10 minutes. Any question? Okay, so let's go for 5 minutes self-study on this problem, try to understand and then discuss among your peers. Okay, at this point, let me open a breakout room for you guys to discuss within the peer. This will be a 10-minute session, and we'll come back with more discussion about this specific problem after that. Hi Joshua, I have sent you a private message over the chat. Can you please take a look? Okay, I think we're out of time for that breakout room. Let me see. Let's wait for a couple of seconds for everyone to come back. I believe, yeah, I think all of you have came back. Okay, anyone wants to, or any group wants to go at least explain the strategy, if not the answer?
I can go.
Sure, Jeffrey, please.
All right, so with when you're calling factorial of 10, and it's a recursive factorial, that means you're gonna have 11 total function calls. And so with each call, we use up 20 bytes on the stack. So at the base case, which will be the point where the most memory is used on the stack, you're
Okay.
gonna be at 11 calls times 20 bytes, which is 220 bytes peak stack memory usage.
Okay. Anyone else? Have any comment on top of that?
So since for the very last call, since you like don't actually use the last 4 bytes that you reserve, would it be considered like 216 bytes since like you never store any data in the very last one at number 220?
Okay, so that's one good point. We possibly need to consider that. Okay, let me at least give you the general guideline there. Jeffrey, your approach is right. I think you need to tune up a little bit at the end, last call, when we don't pick up that that extra byte we add for the double word push boundary.
Got it.
Yeah, so let me explain that to you, and let's also like at least fact check what is going on there. So with these problems, we want to do this thing, right? First of all, remember like I showed you like a function has these parts of the body, like at least conceptually. So first we want to go and try to figure them out, right? So it seems like this part is my RT storage, and this part is my body, and also this part is my RT restore, right? So from here, what we can see that we are basically moving it by 20 bytes, right? Also look at this part. This is like we are storing how many variables? We are storing like 1, 2, 3, 4, 5, 6. 6, no, not 6, 5. Right, so these 5, so I start with a stack pointer to at the call stack, right, which is already pointing to a free location for my data to come in, data to store. So we fill up this data in this process. We are basically filling up from that space with the variables. These are each 4 bytes each, this part. So 1, and 2, Store word. 1, 2, 3, 4. Okay. 4 bytes, 4 variables. So we are basically storing 16 byte. Okay. And moving, so this is 16 byte. And moving the pointer pointing to the 20 byte, right? SP plus, sorry, SP minus 20. So which is basically pointing to a free 4 byte location, isn't it? So let us check our claim, okay? So this is SP, let's say SP was at, let's pick up some random value, 10. So this is 10, this is, so SP, okay, let's start with 80. So SP minus 20 is going to be, this is going to be 60 address. I'm talking about the address. Let's say it started with the 80, then first variable goes on the 80, then address 60, next variable, then goes to 40. Oh, this is 20. Sorry. What am I doing? Just hold on. Okay. These are addresses, minus 4, which is like 76, minus 472, minus 4, 68, right? 68, 1, 2, 3, 4, okay. So basically, remember, this is basically giving you double word boundary push boundary. So stack pointer is moved like 16 byte more onto each frame. So this is extra, sorry, 8 byte, not 16 byte, 8 byte. Extra 8 byte is allocated for a upcoming double word pushing in our strategy. So we are practically storing 16 byte, but we are actually, this is 64, this one is 60. We're actually having some free space. This is free space over for upcoming push. Now, what happened to the next frame creation on the recursive call? So next frame creation would do the same thing, right? It's basically move the stack pointer by 20 points. Then fill up the variable at this point, then second variable, then third variable, then fourth variable. And it is now pointing here. And next frame, similarly, will fill up this first, then this second, then third, then fourth, and this is 16 byte sorry, why I'm saying 16 byte, 8 byte extra, always, right? So you see at the each frame creation, you are actually doing, like leaving one gap with our strategy, right? 1 4 byte extra. So in fact, if your number of call is 10, let's say this recursive call is ended in 10, we'll come back to that one, like to verify how many number of calls will be given. But let's say it is a 10 recursion, number 10 recursion, then each frame or each, no, not frame, I say each iteration will occupy like these 4 variables into 4 bytes plus extra 4 byte for these spaces, right? So that means it is like 16 plus 4 equals 20 byte. All right. And now if it is like 10 maximum depth, then we don't need to accommodate this extra, right? This extra. So this is 8 byte already. So that means what we need to do for the 10, it is 10 multiplied by 20 minus 8 byte. So these are considered as a last frame when it is coming back from the recursion, the last base case. This part is considered as a free space. You don't need to count them. So that's why it becomes like about 200 minus 8. This is about 192 bytes. Question so far on this? Any concern? I may be wrong, by the way. You can challenge me.
I have a question. So if you, like, I guess, look at the top that you multiply by like, so each register is 4 bytes and you have 4 registers plus the extra word of space. So that's 20 bytes for each call.
Mm-hmm.
So if you multiply that, I guess by 10, you get 200. But for the very last one, there's like another 4 empty bytes in the diagram. So shouldn't that be 204? Since the 20 accounts for just the 4 used bytes plus the 1 extra byte. I mean, the 4 used words and then the 1 extra word.
Hey, this is a free space, right?
Yeah.
Like whoever wants to use them, they can use both of them. So our assumption from our convention of this implementation of the function is that with respect to stack pointer, I can push a double word as well if I need. So push double word means it's a 32-bit, 8 byte. I can actually push the complete 8 byte over here. So it's a free space from that perspective.
But like, for example, with what we drew, there's 3 recursive, I guess, runs of this function.
Mm-hmm.
And so the total amount of space that was drawn on here is 5 times 3, which is 15 plus 1, which is 16. Like if you count the number of words that are drawn on this diagram.
Mm-hmm. Mm-hmm.
And then because you don't have the last 2, you subtract 2 words. So then that is 14 words total.
Yeah, I'm not getting it. So let's recount, right? So when we start at this stack pointer, right? It's a free space. That's where we are actually writing. Stack pointer moving by 20 minus, okay, moving by 20 is pointing to here, but we are actually going back and filling up this part. Agree on that part? So this is 4 byte, right?
Yeah.
And then next we are filling up this part, which is 4 byte. Next we are filling up this with next variable, 4 byte. And next we are filling up 4 byte, right? So this is like total 16 byte. And so basically, remember, like this is the first free space to start with, right? If we start associating with an address value like a 80, then -4 is 76, then 72, then 68, right? And SP minus 80 is basically this is 60, value 60, right? So this is basically another 8 byte is consumed. So I think what you are mixing up is this 20. We're trying to do this 20 minus this 16, which is then extra 4 byte. But think to start with, we have this free space. We are actually using that one, isn't it?
Yeah, but like, I guess, so there are 6 words or 24 bytes that are drawn in this table.
Yeah, exactly. So basically, like if you start associating with the addresses, then this concept will start making sense. Okay, so let's start from very beginning, right? So let's say this was my stack pointer, which was pointing to an address 80. Okay, so 80, 81, 82, 83, these 4 bytes will be filled up from that point, right? If something is stored there. And it was moved to SP minus 20, which is a 4 byte address ending here at address 60, like 80 minus 20 is 60. Now we filled up address 80. Then we filled up address 76 with next variable. Then we filled up address 72 with next variable. Then we filled up address 68 with next variable. Then we have another address, like 4 byte address to fill up, 64, isn't it?
Yeah.
So it is not that from 80 to 76 is filled up. It is from 80 to 83 is filled up on this word writing. When you write a word, stored word, it's basically from that address towards upwards. It's always upward. It's not the downwards. Does that make sense?
I guess like, I'm just confused about so for example, since you do like to calculate for 10 recursive calls, you did 10 times 20 minus 8. Because there are 10 recursive calls.
That would be dangerous. That would be dangerous to do. Let's have a thought process on that one. I think we are over the time. It's 7:18 already. So let's stop here tonight and let's continue from this discussion and have a thought process. Can we do this just simply 20 multiplied by 10 and minus something, and that becomes my friend? Let's have a thought, everyone. Think on that process. Is that going to work? Or we should actually go with the real understanding of what is going on in the stack. Okay, we'll pick it up in the next day.
Okay.
Okay, so basically let's stop tonight here. We are over time, like almost like 4 minutes. Sorry for that. And we'll all see you on Wednesday.
Thank you, Professor.
Thank you. Bye.